why don't I finish with this question here, and then we can and then we'll talk about Newton's third law. So here's the concept. I guess you guys can hear this at Livingston. You guys can see this for the first time. We barely got to this before the bell went the other day. So here's the concept. There is an incline. The incline is 35 degrees. And on the incline is a snowboarder. I'll draw a box, because honestly, that's all that really matters here. And we started by drawing all sorts of forces acting on the snowboarder. So one of the forces is going to be friction pulling us backwards. Because friction is going to try to slow the snowboarder down. And, I should point out one thing here. Why is friction going up the hill? Because he's probably going down the hill. That's friction will oppose your motion. It is actually possible for us to give you a question where a person is going up the hill. Like say I've got one in the next set of notes where there's a snowmobile that's actually traveling uphill. Well, in that case, friction would actually be going downhill as well. Does that make sense? So you have to use your common sense as to which way friction is going to go. But I think it makes sense the snowboarder is going downhill. Which I like to call this FD. There's a downward force, basically due to gravity pulling you downhill. Other forces involved. Gravity is ultimately pulling you straight down, but really it's broken up into two different components. One of them is this downward force right here. The other one, I don't really have a great name for it, so I just call it the perpendicular force. Really, the surface itself, the guy is getting pulled into the mountain on a perpendicular angle, and that's being counterbalanced by a normal force. So we got this far yesterday, right? There it is. Okay, sometimes you have to consider physics like a giant puzzle. I was thinking about this as I was driving home yesterday. You guys ever do Sudokus? Like you at least know how Sudokus work. Where you kind of solve in this box for a little while to get a number, and then that opens it up so you can get this box over here. And then that opens it up so you can find this one here. And all of a sudden it just kind of fits together. That's kind of how physics works in a way when you get problems like this. And you are going to get problems like this, right? Where it's not just one-step problems. It's like four-step problems. And it feels like you're using an entire page for one question. Right? It's such a shift from what you've probably done before in the past, right? Where it's not just plug this in as an answer. Right? So working backwards, our goal is to try to figure out the frictional force. Right? So if you like my Sudoku analogy, our goal is like way over here. In order to solve that, we're going to have to use this from this, from this, from this, from this. Like we almost have to like trace backwards a sequence of events. Right? So first thought would be, well, how do I solve for a frictional force? And really, I think the way this will work is that your frictional force, let's start with this. Your F net is going to equal your mass times your acceleration. Right? That's Newton's second law. Right? The net of your forces on the downhill plane. I think I drew. There it is. I drew like kind of something like this here to illustrate the downhill plane we're working with. The forces on that plane are going to be the force of friction and your downward force. Maybe I should write it like this. How much downward force you have minus your force of friction, that'll be your mass times acceleration. Did I get this far yesterday? Okay. So then when I want to talk about other things that are occurring here, to get my force of friction by itself, algebraically, what I could do is I could rearrange and say that FF is equal to, like imagine if I bring this to that side there to make it a positive FF, then I would have to bring this stuff the other way and make it FD minus MA. Last day I kind of suggested that one of the things that you're going to find tricky about physics going forward is you'll ask me what formula to use. And I will try my best to answer it, but really sometimes the answer is there is no formula off your sheet you're using, right? We just kind of piece this together ourselves using, I don't want to call it common sense, but well, I guess common sense, right? Where you have to use your knowledge of physics formulas. So at this point here, in order to solve for friction, then we need to know how much downward force you have, and we need to know how much mass acceleration you have. We have mass. No, we don't even, do we? We have how many newtons a snowboarder is. So that's not even helpful. So we've got one more issue here, is that in order to calculate mass, I have to solve another puzzle here. This right here, this actually is how much force the snowboarder has. Sometimes we use the word his weight. When we talk about how much someone weighs in, I've lost it. When we talk about weight in everyday life scenarios, we actually use the word wrong. Mass is measured in pounds or kilograms. Weight is how much force you have due to your mass. Okay. This right here is really your mass times gravity. That's your weight. It's the amount of force that you have. So whenever you ask someone how much they weigh, and they say, I weigh, I don't know, 120 pounds, whatever it happens to be, that's actually, according to physics terminology, that's actually the wrong way of phrasing it. Mass is in kilograms. Your weight is actually mass times gravity. Does that make sense? Like officially in physics, a weight is a force. It's the mass times gravity. So we've actually been given a weight here, not a mass. That being said, it's actually not that hard to calculate a mass. If the 850 newtons is equal to a person's mass times gravity, how do you get their mass by itself? Divide by gravity, yeah. Divide by 9.81. Divide by 9.81. That'll tell you how much mass a person has. You can kind of see that Sudoku concept here where I'm solving all sorts of little bits and pieces everywhere. Like I'm not even to the point where I'm ready to solve for friction yet. I'm just kind of getting all the setup in the right spot. Oh, good, you guys are back. Yeah, you didn't actually miss much. Verbally, all I was really talking about here is how this 850 newtons is not a mass number, it's a weight number, which is mass times gravity. So over here on the side, we're going to solve for mass by dividing 850 by 9.81 meters per second squared, which is the gravity value. What did you guys get when you did that? 86 I can go with, like that? Okay, so we now know the person's mass. So if I can go down to where I kind of left off right here, I have mass. Excellent. We are part of the way ready to solve the question. We need to know an acceleration and a downward force. So let's do the downward force first, because that one was what we did last day as well. Your downward force right here is part of this triangle, where the 35 degrees is up in the top corner. You guys remember talking about this last time? The more you do this, the more you recognize this is just always the case. Right here in green is a nice little 90-degree triangle. If this is 35, it makes this 55. But then right here, that's 90. So then if this is 35, that's 55, that's 35. So long story short, if I want to solve for FD, I'll do this in green over here off to the side. Just gotta do these like in little chunks. I could say that the sine of my angle is my opposite over my hypotenuse. My angle will be 35 degrees. The opposite will be FD. The hypotenuse will be this side right here, which is the force of gravity. Makes sense. This side right here is the downward amount of force that I'm getting as the guy slides down the hill. But gravity truly actually acts purely downwards. So since this is where my 90-degree angle went, this is the hypotenuse, that's my opposite. So to get FD by itself, you have to take the FG and times up by sine 35. Or mass times gravity times the sine of 35, that's FD. Do I know his mass? Well, I just found it a second ago, didn't I? Do I know gravity? 9.81. So it means that I now have my FD ready to go over here. Still not quite ready to solve this yet, though. I now need an acceleration. So the last thing I'm going to need is an acceleration. But I can use kinematics for this. I gave you a lot of info on this question here. I told you that it begins at rest. So that means your velocity initial is 0. I told you that he slides 14.5 meters. And that the time it took was 6.25 seconds. We should have enough information now using kinematics to solve for an acceleration. So, which formula do we need? D equals VIT plus 1/2 AT squared. So your distance is 14.5. Velocity initial is 0. We'll just skip that. 1/2 of A times 6.25 squared. Solve for A. So take 14.5, times it by 2, and then divide by 6.25 squared. Did you get something? What'd you get? 0.742? Okay. Okay, let's talk about that value for a little bit. If something were to free fall, just straight up fall, what would it accelerate at? 9.81. Okay? But this thing's not free falling, it's on a slope. So if you can imagine, this is a slope right here. I put this guy on there. Is it going to accelerate down the hill? Well, sure, yeah, it's going to fall down the hill slowly but surely, right? One problem is, though, that friction is going to slow it down. Right? A second problem is that it's not straight up dropping, it's sliding downwards, right? So it does make sense that it's still accelerating, but it also makes sense that it's accelerating nowhere near the rate of 9.81. You know what I'm saying? Long story short, I think we finally have all the information we need to finally solve our puzzle. So we started with Newton's second law back here. We kind of pieced together a formula for ourselves to get friction by itself. But the problem is that I did not, at the original time, possess a downward force, a mass, or an acceleration. So that's why off to the side I kind of have 3 different calculations here. This one in purple, I had to calculate a mass. To do that, I took my force of gravity number back up here and I divided by 9.81 to actually get a mass. I also needed to have how much downward force there was, this downhill amount, either one. To do that, I needed trigonometry. To solve this, I also needed mass again a second time, so it's a good thing I started with mass. And then the last thing I needed was an acceleration. But now, hopefully you'd agree, we have all the information we need to solve this thing, right? So to find the force of friction, we need to know our downhill force. Oh, did anybody actually calculate this amount right here? What would this be here? It would be that 86 number times 9.81 times the sine of 35. 487? Okay. So I'll just let you fill in the blanks. So that's 487 or so newtons minus 86 times 0.742. That's how much frictional force that would be. We get 2 sig digs. You guys have a final answer? .2 times 10 to the 2. Okay. So that would be like 420-ish. And then he made it 4.2 times 10 to the 2. You guys get that as well? Okay. That makes sense. It's a lot, hey? You can kind of see why our physics class has gotten whittled down slowly but surely. Because this is why this is why physics is often thought of as being one of the most difficult sciences, right? It's not just that you have to have good math skills. I mean, you have to have good math skills to solve these things, right? But it's not just that, right? These are not one-step problems that you're going to solve. And this is not unusual. This is not atypical. This is the sort of thing that I think pretty much every Physics 20 student would get. So I'm not actually making it really, really hard for the sake of that. This is just normal expectations. You've got this puzzle to solve, You have to try to find this number up here, and this number over here, and this number over here, and finally put them all together into another makeshift formula. Right? And that's kind of where this goes. Physics would be really easy if all you had to do is just take a formula and plug just 3 numbers and then solve for the 4th, right? Everyone would take physics if that was the case. The hardest part about this is that can you wrap your mind around it and figure out how to solve the puzzle. The more you do it, the better you get, right? And the more that you kind of get used to the concept of treating it like a puzzle, I think the better it gets as well. That makes sense. How about you guys? Were you able to follow that example? Okay. Did you do the calculations as well? Did you get 4.2 times 10 to the 2? Okay. Okay, cool. Okay, let's move on then. Let's start talking about Newton's third law then. So. That won't help. No, you need a calculator. Okay, so Newton's third law, if you've looked through the notes at all, today I'm going to do 2 main things. I'm going to talk theory-wise about a whole bunch of pictures, kind of like I did with Newton's first law, and then after I do that, then we're going to do some more calculations. So it's kind of more of the same for the math, but before we do that though, I need to make sure you fully get the concept. So let me do a quick recap while they're out grabbing stuff. Newton's first law, inertia. Objects in motion stay in motion. Objects not in motion are not in motion. My water bottle has been sitting on that table since last night. And it's going to sit there until something causes it to move. Does that make sense? It is not in motion. It is not going to move, right? It's not going to randomly just grow legs and walk away, right? That being said, if there was an earthquake, would it fall off the table? Sure, but that's because there's some sort of force acting on it, an unbalanced force. Right? There are actually forces acting on my water bottle as we speak, though. Gravity is pulling it down, but the normal force of the table is actually pushing it back up. If that table were really, really weak and fragile, conceivably, I guess the normal force of the table could fail and the table could collapse. I doubt that table is going to break because of my water bottle, but you guys can imagine that if like 5 of us stood on the table, it would probably break. Does that make sense? So that's Newton's first law. Objects in motion will stay in motion, objects at rest will stay at rest. Newton's second law is kind of the fulcrum of all the math we use. F equals ma. I like writing in that orientation. I know your data sheet puts it as like, what was it, A equals F over M, the way they write it. It's the same thing, really. Newton's third law is the retaliation law. That's how I like to remember it. Basically, the concept is for every action, there's an equal and opposite reaction. You guys have probably heard that phrase before, right? So I've given some examples of this previously. Let's go through some slides. Here's a picture I like. Well, imagine that you are stepping off of a boat. Maybe you've even experienced it before, right? If I step forward, the boat is actually going to go backwards. Okay? I managed to stick the landing last time. Okay? So if I step forward off of this, the chair goes the other way, right? I know I kind of exaggerated it a little bit, but that's the concept, is that there is always an opposite force, right? The opposite force to gravity right here is the normal force. If you have an applied force going forwards, often there's a force going the other way, friction. So let's talk through some more pictures here. How does this illustrate Newton's third law? In order to get this rocket ship to go up, right, it pushes down, yeah, right? Really, if we're trying to go up this way, if you have an applied force, I'll just say force applied going up, really what's happening is the exhaust has to go downwards, doesn't it? Right? Does that make sense? I can't have the exhaust of the rocket ship coming out the side. If the exhaust of the rocket ship came out of the side, right, imagine that somehow the vent was this way, the rocket ship would not go up. The rocket ship would go this way. Doesn't that make intuitive sense? Right? So because the propellant is getting fired backwards, the rocket ship goes up. How does a boat propeller work? What does a boat propeller do? Yes, it pushes the water backwards. Right? And because it pushes the water backwards, then the boat goes forwards. Does that make sense? That's really how the concept works, right? As this thing spins around, it is pushing water in a backwards direction. And because it does that, Newton's third law propels the thing forward. Very similar to the first example I've given for some of you of someone shooting a gun, right? A gun has a recoil. As the bullet goes out of the gun forwards, the gun recoils back towards you. That's Newton's third law, right? Same concept here. Alexander Ovechkin is going to shoot a hockey puck. I couldn't actually find the photo exactly that I was looking for, so you'll have to kind of bear with me as I describe it. Has anyone ever seen like a picture of a hockey stick flexing before? Right? Where like as he's shooting the puck, like the hockey stick is normally supposed to be flat like this, right? That's actually not a bad hockey stick. Right? But have you ever seen a picture where like it is wicked bent, right? As he's like slamming the stick into the ground, and it's got that big flex to it. You know what I'm talking about here? Right? And that's almost kind of the same thing there, where he's got so much force pushing into the ground that when he finally manages to like break through the amount of friction there, it actually flings the puck forward. Maybe I'm not using this example quite the way I'd like to, but isn't it the same thing as like when a baseball pitcher is throwing, right? Remember in the movie we watched there, when he threw the ball, he went backwards. Remember that there? Well, but that's not what happens in real life, because when he pushes against the ground pushes back. Does that make sense? Right? When I push against the ground, I don't slide backwards because there's enough friction there to maintain it, so the ground pushes backwards. I was going for the same sort of thing here. When you get the flex in the stick, really what happens is when you push down on the ground is also pushing back as well, right? And it causes the stick to flex until eventually the friction force is not able to maintain it anymore, and it flings the puck towards the net. Does that make sense? So there's kind of Newton's third law kind of hidden in there too, where the ice is actually pushing back on his stick just as much as he is pushing on the ice. Think of that next time you score a goal, okay? Okay, here's a picture of a book sitting on a table. Is it actually even in motion? But Newton's third law still applies. The book is getting pulled downwards by the force of gravity. Right? I mean, gravity is acting on the book. We've talked about this before, though. What force is the opposite equal force to it? The normal force of the table is pushing the book back upwards. If this book were 9,000 pounds, it is possible that the table is not capable of withstanding that amount of force, right? But so long as the table is actually structurally strong enough, these two things will be in equal amounts. Should your normal force ever be more than your gravitational force? Then your book would start to levitate. And that doesn't make sense, does it? Right. So your normal force, it's maybe best to write it like this. Your normal force can be less than or equal to your gravitational force. Right? It's not possible for your normal force to be greater than your gravitational force. That would be true. If it's equal to it, then it just kind of stays at rest. If it's less than, then it means that your structure is probably breaking. Right? All right, and then last one, just for silliness here. How does this illustrate Newton's third law? Someone's playing a prank. That's what I was going for here, right? Where someone decides to put shoe nail polish on the phone, and then someone else puts Vaseline on the doorknob, and then it escalates, and then someone covers someone's entire workstation with paper. Hence the retaliation principle. So, I did this once in university. It was fun. We filled someone's entire dorm room with paper. Yeah. Crumple up newspaper. So, anyways, obviously this is not the same sort of thing as Newton's third law, but can you use it as a way to kind of remember the concept? I call it like the retaliation one, right? When something happens here, there's an equal and opposite force happening the other direction, right? As I shoot the gun this way, the amount of force that gets shot this way is the same as the recoil going this way. There's actually a question like that on your assignment. It's actually, Derek, was that the first one? The one with the shooting of the gun? Okay. Let's talk about how this would look mathematically then. You could then say that the force going forward has to then equal the force going backwards. You could do something like this. Based on that, this would be like the mass of the bullet times the acceleration of the bullet would have to equal the mass of your gun times the acceleration of like the kickback in your gun. Now, the bullet travels really fast, right? But it has a very small mass, right? Which is good because your gun has a fairly large mass, so therefore the acceleration of the kickback is not quite so high. Imagine for some possibility that you were shooting a gun the size of the bullet. So again, let's say that you shot a bullet, but the gun you were shooting was the same size as the bullet. Well, if the bullet goes really fast that way with acceleration, your gun would kick back at you just as fast. So that'd be a problem, right? Because then you'd basically put a hole through your shoulder as you shot. So that's kind of why it's good that you have a small bullet and a large gun. But anyways, this is kind of the setup as to how you solve that first question. So let's try some more math questions in a second here. I know I'm getting close to that spot. Here's some more pictures, just illustrating the same concept here. Let's just talk through them here. The ball is going to hit the volleyball player. But really, the volleyball player's arms are fairly strong, unless your arms are so weak that as a volleyball hits your arms, they break both of the bones in both of your arms here, right? What's really happening is as the ball applies force to your arms apply force back to the ball, and hence it pops back up in the air. Does that make sense? Or the bat is going to exert a force on the ball, but the ball actually exerts a force on the bat. Or the student is going to push off of the ground, but really the ground is actually pushing back at the student. As I jumped, I pushed myself up, but I actually pushed the ground down. Okay, now did the earth actually move? Well, but here's the thing. How much mass do I have in comparison to the earth? It's like that bullet example again, right? My mass is so incredibly small that really what is happening is I am pushing myself up and I'm pushing the earth down, but the earth moves nothing, right? Because I am so little in comparison to it. But I mean, is that not any different than this example here where this is me, this is the earth, and now when I push off of it, that was poorly done. Now when I push off of it, right, I went one way, it went the other way. Does that make sense? So in a way, the student is exerting a force on the ground, but the ground is exerting a force right back on the student. Does it hurt to fall? Let's say you fall from a really far height. Does it hurt you to fall? Or does it hurt you to land? Right? And that's what I'm going for on this last one here. Well, this is actually what the picture says, but let's say when you're falling downwards, really, what happens is the apple is going to exert a force on the ground. In a way, you can think of it as the apple is trying to bruise the ground. Is it going to be successful in its job of bruising the ground? Probably not. But the equal and opposite force is the ground is going to bruise the apple back. Who's going to feel the brunt of the force more? Well, the apple, right? Does that make sense, though? No. But I mean, change the scenario. Let's say that I use a jackhammer. Oh, you guys are out? Okay, we'll talk to you another day. Let's say that I use some sort of big hammer to try to, like, crush the ground. They have to leave early today. So they have something. So, well, let's say that I actually take, like, a hammer and try to hit the ground. Isn't the same principles apply? The hammer is trying to break the ground, but isn't the ground also equally trying to break the hammer? If that makes sense? It really just depends on what you're using. If I use an egg to try to break the ground, I'm not going to do very well because the egg won't be able to withstand that sort of force. But if I use a jackhammer to try to break the ground, now maybe it's the ground that can't withstand that sort of force. You know what I'm saying there? So, long story short, equal and opposite reaction forces. Okay, let's do some examples with some math. So this is where the fun comes. And by fun I mean no. Because we're gonna have numbers everywhere again. So. Okay, we've got a truck tire, and the truck tire is on a horizontal frictionless surface. Just to make it a little bit easier, we're gonna make it so that there's no friction here yet. Obviously there will be friction, but let's just remove that dynamic from the equation right now. You've got a bucket, pail B, and you've got a bucket, pail C. We've kind of done something similar to this before. What's going to happen? Is it going to just stay stationary? which way is it going to move? Is it going to move towards our right or towards our left? Towards the right, I'd agree. And hopefully you intuitively can figure that out, because really what's happening is there's a force of gravity being applied here, which is based on the 5.6 kilogram bucket. But there's a force of gravity being applied here based on the 8.2 kilogram bucket. Well, 8.2 kilograms weighs more than 5.6 kilograms. Use the wrong word there. 8.2 kilograms masses more than a 5.6 kilogram. That's actually the right word we should use. It has a higher mass. Because it has a higher mass, though, it does have a higher weight. That's actually still true. But anyways, you gotta get the point where I'm going here. So let's draw a free body diagram. Okay, here's my object. Rather than trying to draw things going around a corner, though, would it make sense to say that I've got a force of gravity, 1, pulling it this way, essentially, but I have a force of gravity 2, pulling it back the other way? Does that make sense? I'm getting pulled one way, I'm getting pulled the other way. It's a tug of war. I'm fairly confident that FG1 is going to win because it's got more force on it. We actually start where we did the previous questions. We're going to start with Newton's second law. The net of all of our forces is going to be mass times acceleration. There's actually more forces in play here, though. They just don't matter to this example. But would it make sense that there is a gravitational force pulling the tire downwards as well? Right? And then there's a normal force because the table is actually able to withstand that tire. The table's not so flimsy that it's going to break. But I don't actually need to care about this direction here. I care more about these other two forces. So I could now piece together an even better formula that says that the Fg1 minus the Fg2 must be equal to the mass times the acceleration. I can even take it one step further than that. How do you calculate the force of gravity on something? Force of gravity is mass times gravity. So this would be the mass of object 1 times gravity. This will be the mass of object 2 times gravity. What about this mass right here? Is that the mass of object 1 or of object 2 or of the tire? It's actually the mass of everything, right? Because this is the mass of the entire system. We're just going to treat this all as one big object. I know it's tied together by ropes, but really, can we not just think of this all as right here? This is all just one object. So the mass of the entire object is 20 plus 5.6 plus 8.2. So they get 20. Thank you. So this is like the mass of, I'll put an E for everything, I guess. There's no right or wrong way of dictating how you keep track of it. You just need some method that works for you. We need the mass of everything. Can I throw one more thing on here? This is the acceleration of everything as well. Won't all of these objects all be moving at the same speed? This bucket here will not be moving faster than this bucket here. They're all going to be moving at consistent speed. Think of it as, like, say, a train. This is really the lead car of the train. This is the middle car of the train. This is the caboose of the train. I know they're going around a corner here, but aren't they all going to have to be going the same acceleration? If the first car was traveling faster than the second car, wouldn't the coupling eventually snap? Or if the last car was traveling faster than the first car, wouldn't it, ram into it? So in a way, all three of these independent objects, I know that they're kind of independent, but they're really all going the same speeds, aren't they? Well, there's not one that's going faster than the other. So, okay, we're looking for the acceleration of the system. So we're looking for this guy here. So now I need to work backwards and see, do I actually possess all the rest of these numbers? And I think we do, right? Because this one is 8.2 times 9.81. This is 5.6 times 9.81. And this is, what did you say it was again? 32.8? 33.8. Times the acceleration of like everything. Because everything's moving the same speeds here. So now it's just algebra. Times these minus these, divide by 33.8. And that'll get you the acceleration of the whole system. You guys get anything? What'd you get there? 1.75? 0.75. Okay, we're all on the same page on that?
I got that.
You got negative, right? Okay, did you do the 8.2 times 9.81 first and then minus the 5.6 times 9.81? Or is there a chance you did the 5.6 first and then the 8.2? Okay, this is actually a really good talking point. So, Andy, what you did is it seems like you made this be the positive direction because you placed that one first, and you made this be the negative direction. Does that make sense? Because you essentially started with this one and then subtracted this one away, which is why you had a negative number, because according to the way that you've orientated this, the acceleration is going towards the negative side. But the way that I've done this, and I imagine everybody else has, is we made this one kind of be the positive one, right? Like this one's the positive one. This one's the negative one. Therefore, our acceleration was a positive number because it's going in what we've defined as the positive direction. Does that make sense? So, I mean, numerically, it's not wrong. You just need to make sure that you know which direction it's going. Maybe I'll say that it's going towards the right, just to make sure it's clear then, right? Because it's accelerating that way. It's actually really not true, because one bucket's actually going up, the other bucket's actually going down, and the tire is going to the right. But does that at least make sense? Okay, questions so far? Okay, that's actually really not Newton's third law, that's Newton's second law, the force equals mass times acceleration. But a very typical question you'll get asked about is tension. So I'm just going to do a little erasing if I can here, so it's not so busy right here. This rope right here has a certain amount of tension in it. Let's say that I used something strong like a chain or a rope. I feel like the bucket would be able to withstand that sort of force on it. What if that rope there was made out of dental floss? It might snap, right? Well, isn't that kind of Newton's set third law, just like with the table analogy? My water bottle right now is really not in fear of breaking through that table because the table can withstand that amount of force pushing back on it, right? But if that table were made out of paper, we might have a problem. That same kind of logic would apply here. If my rope is made out of something fairly strong, it has tensile strength to it. If it were made out of Spider-Man's webbing, we're good. Silly, right? But if it was made out of, well, a single strand of nylon, it's gonna snap. Does that make sense? So we can actually calculate how much tension is in that rope to make sure that we actually use a rope strong enough to withstand this. So that's where Newton's third law kind of comes in. So can I erase what's below there? We don't need that again. So I want the space. So give me a second. So rather than treating this now as one big object, it's actually best now to treat it as three independent objects. So now we do have this object, now we do have this one, and now we do have this one. So I'd like to talk about them one at a time. So I'm going to work with this one over here, pale B. What forces are acting on pale B? Well, just purely on pale B, hopefully you'd agree that gravity is pulling it down, right? But is pale B going to actually go downwards? No, we actually know that pale B is actually losing this fight to pale C. It's actually getting pulled upwards. So in a way, the other force is not a normal force. We often call it the force of tension. There's tension in this rope right here that is pulling it up, kind of like an elevator would be, right? So long as the elevator cable is capable of handling the force required here, that's a good thing, right? I don't want my elevator cable made out of dental floss. That'd be bad. I would go plummeting to my death, right? I want it to have a strong tensile strength. So there must actually be more tension than there is gravity. So now I want to work with just the free body diagram of Pale B. Well, if I work with just its free body diagram, then I could use Newton's second law again and say that the net of all forces equals mass times acceleration. But now I'm considering just that one Pale. Well, what forces are acting on Pale B? Well, there's tension, which is going to win, minus gravity equals mass times acceleration. Would it make sense algebraically then to say that my tension will be equal to mass times acceleration plus the force of gravity? I'm just throwing Fg on the other side as a positive. Okay, so let's solve the puzzle. Do we know the mass? Okay, well, hang on. Mass of what? The whole system? Or just the mass of just the bucket? Now we're considering only the bucket. So this mass right here is now the, what is that, 5.6. Do we know its acceleration though? We just solved it, didn't we? Right? All three objects are accelerating at the same rate. So that's why we actually need to solve it. Its acceleration was 0.75 or whatever you discovered. But we need to add onto this the force of gravity. So the force of gravity will be mass times gravity. So its mass will be 5.6 again, and gravity will be 9.81. Was that exactly 0.75 or was it a rounded number? Okay, so make sure you use the rounded number, obviously. But this will tell you how much tension is on this rope here. And good eye. Say it loud. 59. 59. Okay, 59 newtons. Okay. So here's what this would mean then. This rope right here better be able to handle at least 59 newtons worth of force on it. Its force is not just purely due to gravity, but it's also due to the fact that it's getting pulled in two directions. Right? And this rope, really, it's getting pulled this way around the corner, but it's also getting pulled down due to gravity. So this is actually the rope that has quite a bit of tension on it due to two things one pulling it this way, right, and one pulling down. It's like the friend that's getting pulled both directions. Does that make sense? So this guy better be able to withstand quite a bit of tension. Is that a question?
Is the acceleration still positive if it's going up?
Yeah, does that make sense? Because of the fact that we've denoted this as being positive, we'll make the acceleration be positive.
If the other one's being negative?
Ooh, good call. I'm just wondering whether the reason why I think it won't on this one here is because see how I made it a negative force of gravity right here? I've already accounted for that. That's a good question though, right? Because see how I made the force of gravity be negative? I've already put it in the negative direction down here. Good question. If I did it twice though, if I put an extra negative in, that would screw it up. Right? I guess what you could do is you could do Ft plus Fg. And then what you could do later is you could throw in the negative 9.81 to indicate that it's the negative 9.81 is going that way, and that one's going upwards. That's a good question. Does that make sense to everybody else? So I have accounted for the negative. I just did it earlier. I did that. Apparently I can't undo. There it is. I did do that right here because I made the force of gravity be negative right here. Okay, so tension is actually a positive tension going upwards. Gravity was a negative going upwards. That makes sense? Okay, let's calculate the tension on the other rope now. So this rope over here, the way to calculate that tension would be to draw a free body diagram for Pale C. So I'll draw it over here just because it's on that side. And honestly, it has the exact same scenarios, doesn't it? It has a force of gravity pulling it downwards. It has a tension amount pulling it upwards. But actually, just like Rebecca mentioned here, we've got to be really careful with our pluses and minuses this time. as to how this works. So if it's okay with you guys, I'd like to denote the force of gravity as being in the positive direction. Even though gravity is pulling it down, let's make that positive, and let's make tension be negative. So when we write this one out now, I'm going to say that the net force is equal to mass times acceleration. I'm going to say that the force of gravity now needs to subtract the force of tension for mass acceleration. That makes sense? Last time it was tension minus gravity. This time it's going to be gravity minus tension, just based on the orientation of how this works. To get tension by itself, does it make sense to flip tension to this side over here and bring mass acceleration back the other way? So to get tension by itself in a formula, it'll be the force of gravity, minus mass times acceleration. See how last time it was mass times acceleration plus the force of gravity? Last time it was ma plus fg. This time it's fg minus ma. Let's talk about why. On this example right here, tension's pulling it up, gravity's pulling it down. That makes sense? Right. Really, it's getting pulled in both directions. But here, on this one here, gravity's pulling it down, but isn't the acceleration of the system kind of also going downwards in a way? Right. And but the tension is pulling it backwards just slightly. So there might actually be less tension than there was before. We'll see how this turns out. The force of gravity is mass times gravity. So that's what is this? 8.2. There it is. 8.2 times 9.81. And we'll minus 8.2. And then the acceleration, isn't it still the same acceleration as the other bucket? Aren't the bucket and the tire, they all going the same way? So then that one should be 0.75. What'd you get? 74? So again, kind of similar to the last one, gravity's pulling it down, but there's resistance pulling backwards, right? It's like you're getting pulled in two directions at once here. Does that make sense what I'm saying? So let's try one more thing here. Let's try the free body diagram of just the tire. And let's see how that works. So we do the tire. How is the tire being pulled? Well, the tire is being pulled this way and pulled this way. But rather than say that the tire is being pulled by gravity, is it fair to say that the tire is being pulled by 74 newtons that way? Because that's the tension in that particular rope. But it's being pulled backwards by 59 newtons this way. Doesn't this make logical sense that this one here is bigger than that one? Because which way was the tire actually going to end up going? It was going to go that way, right? It's because the tension in the rope right here is actually bigger than the tension in the rope back there. If I were to actually try to solve this, F net equals MA. I just want to try something. I didn't plan on doing this, but would you agree that you could take 74 newtons and minus 59 newtons to find the net force? His mass was 20, right? So if I were to make it divided by 20, what should the acceleration hopefully be when I'm done? 0.75. Shouldn't it still be the same acceleration that we calculated the first time we did it? So maybe try that real quick if you can. Find that 74 number, whatever it was. Find the 59 number. I really hope this works. It should. All right. Subtract them and divide by the 20. That should be the acceleration of this guy, because really all three objects have that same 0.75 acceleration. So here's the advice I give on a question like this. you have to treat it at first as though all objects are combined as one big object. You have to use that to solve for the acceleration. Then you can break it up into pieces, because each individual object, you can work on its free body diagram, but now you know all of their accelerations, because the acceleration of this object is the same as this one, is the same as this one. So treat them all as one big group to start with to find all of their accelerations, and then treat them all individually as you need. I was kind of thorough on this question. I didn't actually need to do the last step here. I just wanted to prove to you that it would work. That makes sense? I say this in math a lot. I think there's 3 stages of understanding. The first one is went over your head. Hopefully you're not that stage too much here. The second one is you could follow. You guys feel like you more or less were able to follow what I did there? The third stage is the hardest one. It's like, can you do it by yourself? Yeah, we're not there yet. We got time, okay? So let's do a few more examples though. So, let's try another one. Repetition helps promote reinforcement. Okay, this is almost the exact same as a question on your assignment. Do you guys have assignment number 1 printed off? If you happen to have assignment number 1, take a look at the bottom question on it. It's going to look almost the exact same here, where you've got a guy pulling a box. That box is pulling another box. You with me, Joe? Okay. This is a scenario that I'm going to make sure you encounter during this unit quite a bit. The example I might give would be, this is a train, and it's coupled to a car. And that car is coupled to another car, which is coupled to another car. Or, for example, this could be a truck, and the truck is pulling a trailer behind it. Does that make sense? Really, any object scenario where you have one object and a second object, which could be decoupled, or they could be linked. That's this kind of scenario. Does that make sense? So we'll just do boxes, though, to keep it simple. So here's the scenario. You have a 2-box system is pulled using an applied force. The 20-kilogram box experienced friction. This is what we didn't do last time. We got to account for friction now. Yay. The 10-kilogram box experiences 4.3 friction. So let's do the exact same thing we just did. We're going to find acceleration, and then we're going to find tension. Okay. So first thing we should do is draw a free body diagram for like the whole system. How much weight would the whole system have? How much mass would the whole system have? Yeah, so all I do is write it here. I'm dealing with both of them collectively combined at 30 kilograms. Okay, I know that gravity is pulling it downwards, and I know that there's a normal force going upwards. And not that you're looking forward to this, but I promise you those will actually be relevant in further questions. We actually have to use that at some point, which you can imagine just makes the questions even more complicated. Yay. But we can skip them for now, but get in the habit of recognizing that. Okay, we've got an applied force pulling us forward at 50 newtons. But there's friction. Well, if the applied force is pulling us one way, then isn't friction going the other way? But I actually have to draw 2 lines, because one of the boxes has 6.7 newtons, and the other one has 4.3 newtons. I could add them together and just draw one collective line if I wanted to. But I think I'll do them separately just to make sure it's clear that really there are 2 things slowing it down. This guy is being slowed down, but this one is also being slowed down, right? They're both being slowed down. Okay, so this is where, it's at this point here where kids often get stuck. And it's hard for me as a teacher to know how to guide you to the spot without just telling you what to do. But for right now, I'll just tell you what to do. Start with Newton's first second law. The net of all your forces is equal to mass times acceleration. It's kind of the base place we start with, right? Well, what forces do you have in play? If it's okay, I'm just going to kind of skip a line here. Would you not agree that you have 50 newtons going one way? But you need to subtract 6.7 going backwards, and you also need to subtract 4.3 also going backwards. I mean, you could write out, you know, F1 and F2 for the 2 different forces of friction. mass acceleration. I'm going to skip a step here if it's okay as well. To get acceleration by itself, I just divide by mass, right? The mass, though, we're treating the whole system collectively here. So we need the mass of everything, which is 30 kilograms. So here. Now I can find the acceleration of all of the objects. Because both objects are accelerating at the same rate. If one falls behind, then that rope is going to snap, right? If, makes no sense, but how can the second box actually go faster than the first? That doesn't make sense. 50 minus 6.7 minus 4.3. If you do it all in one step, don't forget to put a bracket around the top, or do it in stages. $9.3? 1.3. Everybody cool with that? Okay, well, that's the start. We need to know the acceleration of both boxes. They're both accelerating at the same rate. But then we want to try to find the tension in the rope. Now we can do this in one of two ways. We can either focus on the 20 kilogram box just by itself, or we could focus on the 10 kilogram box just by itself. Either way, it should work out if the question's been designed properly. So why don't I do the 20 kilogram box first, and then we'll check with the next one. So let's deal with just the 20 kilogram box now. Often what I'll do for my three body diagrams is I'll put the mass inside my square, just so that I know which object I'm talking about, whether it's object 1, object 2, or both of them. It's my way of keeping track. So, wait, what forces are in play on the 20 kilogram box? Well, friction's pulling it backwards. Is the applied force actually being applied to the back box? So then what's actually pulling the back box forward? Tension in the rope, yeah. Tension in this rope is pulling it forward. Okay, that's all I need. So then you ask me, Chris, what formula do I use? And I go, well, start with Newton's second law and then try from there. If you want to actually write out F net equals ma, you can, but after a while, hopefully you just get better at recognizing, isn't it going to be just tension minus friction equals mass times acceleration? Can't you kind of like skip a step if you want? And if I want to even skip another step, it'll be friction plus mass times acceleration to get tension by itself. This is the hardest part. This is where I find kids struggle the most, is how do I make myself a formula? Does that make sense? And now to start plugging numbers in. Do we know the force of friction being experienced only by the 20 kilogram box? Yeah, it's 6.7. Do we know the mass of the 20 kilogram box? Well, yeah, 20. Do we know the acceleration of the 20 kilogram box? Yeah, we just found it. Yeah. I'll tell you how much tension is in the rope. Does it make sense that these two numbers should be added to each other? Isn't this same sort of thing again? Right? You're getting pulled this way by one, but you're kind of getting pulled this way by the other. So you kind of have like two things that need to get combined together to get your tension. In terms of positives and negatives even, the reason why we're going to use a positive acceleration here is because I'm going to make this be the positive direction and this be the negative direction. So it's kind of like I put a plus in front of the tension, I put a negative in front of the friction, and so I'll put a plus in front of the acceleration. Does that make sense? It's kind of back to like your first question there, pluses and minuses. What'd you guys get? You gotta say it way louder. So sig digs, we get 33? Okay, we can stop there, but I want to just confirm that we can actually solve this a different way. It won't take very long. Yeah, we should, I guess. Let's say that the tension is going, well, actually no, tension is going to be tricky here. Because of Newton's third law, one box is getting pulled forward by the tension, but the other box is actually getting pulled backwards by tension. So I think on this one here, I probably would kind of skip, or at the very least, I would just say find me the magnitude of the tension. Because this is actually what I want to talk about on the next question. Well, what if I use the 10 kilogram box? The 10 kilogram box is getting pulled forward by the applied force, but it's getting pulled backwards by tension. This is where Newton's third law comes in. The tension is really acting in both directions. It's pulling the one box forward, but it's actually pulling the other box backwards. Does that make sense? So it's almost kind of hard to give a direction to it. I think the better way to put it would be the tensile strength of that string better be at least 33 newtons. If it cannot handle 33 newtons, the string will snap and you're going to have a problem. So let's try it for the other box. If I designed the question correctly, which I really hope I did, the math should come out properly. Like it should be the same number. Right?
Where does the friction go on this?
Ah, good point. Friction also pulls backwards. Thank you, I almost missed that. Right? Because you have an applied force going forward, right? But this box right here has tension pulling it backwards. It also has friction pulling it backwards, right? Good catch. So, I mean, if you really want to write it out officially, starting from the top, it would look like this. But I would say, well, you have an applied force in a forward direction. You have a tension force in a negative direction. You have a friction force in a negative direction. And that's your mass acceleration. Okay, I'm going to look for tension again. So I know we just solved for it, but I want to prove it a second time. So to get tension by itself, I think the easiest way of doing that is to flip those ones around. So take your applied force minus your friction, also minus your mass acceleration, and that should give you tension. And as long as I've designed the question properly with the right numbers in the right spots, we should get the same value we just got. So let's give it a check. The applied force claimed it was 50 newtons, and the friction was 4.3. So that's 50 newtons, that's 4.3 newtons. The mass of this box is 10 kilograms, and we know it's acceleration because we solved for that a while back. I hope I did it right. You got something? Okay. At some point I can kind of, as a teacher, I can see when things are clicking a little bit for some students because once you get the puzzle set up, the math is the easy part almost. And you guys are kind of the fortunate kids who you can handle the math, because not everybody can even handle the math required in physics. But at a certain point, I promise you, you'll get to the spot where you'll be happy to be like, oh, look, calculations. I can do calculations. I mean, they suck because it's just a lot of numbers, but you're very good at that. The hard part is just, how do I get to that point? Does that make sense what I'm saying there? But I imagine that for a lot of you, by the time I got to the step where I was right here, where we kind of made our own formula, you're like, oh, well, I have this, I have this, I have this. I can do this now, right? A lot of kids, they still struggle with that, obviously, right? And so that kind of makes physics harder after that. Okay, questions on that one? Okay, I think I have time to do one last example. We'll do the snowmobile example. We're now going to put everything together. So we're going to have tension in a rope. We're going to have friction, but we're going to put it on a hill. So we have to deal with things in multiple different directions. If you can solve this, you can do anything. Because this is really like the creme de la creme. This is the mountain. Okay. So the basic premise, though, is the exact same as we've been doing all before. So to start with, let's draw a free body diagram. Only today's free body diagram is actually two boxes, really. You've got a snowmobile, and the snowmobile is dragging cargo. You guys can maybe see where this overlaps with our previous example here. This little rope between them is the tension. If that tension becomes too much for the rope to handle, the rope snaps, and all of his supplies go sliding back down the mountain, and right, you know what I'm saying here? But for right now, to begin with, can we treat this all as one big object? And later we'll treat it as two separate objects? So for right now, its combined mass is 1,050 kilograms. This is 1,000 kilograms. This is 50 kilograms, but its combined mass is 1,050 kilograms. Okay, in terms of forces, the snowmobile itself, I know it's not being dragged by a rope, but it has an engine which is propelling it up the hill. I like to call that an applied force. I know there's tension in between these two objects, but let's just ignore that temporarily because we're just treating them as one big blob. What is making this thing go back down the hill? Friction? But that's not the only force. Yeah, let's call it FD, the downward component of gravity. Okay, may as well get in the habit of doing this because you kind of always need to do this. You need to draw in that extra triangle. This is FD, this is FG, this is F perpendicular, which we'll get to. Our angle was 25 degrees, so that means the 25 degrees goes right here. You okay with the setup so far? First, you got to wrap your head around what's actually happening. Then, you got to try to find a way to make yourself a formula. I really mean it when I say you need to make yourself a formula. Okay. It's different every time. If you need somewhere to start, F net equals ma. What forces do we have? I feel fairly comfortable in saying this thing's going uphill, right? So let's start with the applied force. We'll make it a positive applied force. Let's subtract some friction. Let's subtract some downhill force. And we'll make that mass times acceleration. I haven't even looked at a number yet. I'm actually kind of doing this on purpose, right? I'm skipping all the numbers until I can get to the spot where I can use something. So, okay, what am I actually being asked to solve for? Okay, acceleration. So let's walk through what I need then. I need to know the mass. I think I have that, right? 1050. I need to know the applied force, 5,300 newtons. I need to know my frictional forces, 500 newtons. So I have this, I have this, I have this. I don't have FD though. That being said, FD is the same every time once you get used to the habit of it. The way it works is that it's mass times gravity times the sine of theta. That's your FD. Honestly, guys, after you get the hang of it, you can just do that every single time. If you need me to prove it to you again, I can do that, right? It's sine of theta equals the opposite over the hypotenuse. You're just timesing FG up, which is mg. So, okay, let's give it a try. The applied force was 5,300 newtons. We're going to subtract some friction. Friction was 500 newtons. We're also going to subtract the downward force, which will be mass, 1050, times gravity, 9.81, times the sine of 25 degrees. That'll equal your mass, again, 1050, times the acceleration. So divide out 1050. Hopefully you're at the point now where, as I'm solving this question, you're going, okay, now that I got the setup right, the math is just, oh, here, I just type some numbers in. Hopefully. I just don't make a mistake like this. Did you guys get the same thing? What'd you get? 0.425. Thank you. 425.
rounded it and stuff.
Okay. You guys are going to use that value later anyway, so. You guys get that as well? Okay, so there's part one. We now know the acceleration of the snowmobile and its cargo going up the hill. Which is, I mean, on its own, that's a question, right? When you guys get stuff like this, it's often going to be linked questions. 1 year on the diploma, there was a question that had 8 parts linked to it. It was insane. It was use this next information for 8 questions. So it's a very common thing to happen. So that's why I'm going to show you them right now. I'm not gonna tiptoe around it. And it kind of sucks because if you screw up part A, it might screw up your part B and C. You know what I mean? Well, for that particular one, it was like use this information for the next like 8 questions, but you had like some of it answered A, B, and C, and then you did like some other stuff which was like kind of half independent for the next little bit, if that makes sense. So I don't think I've ever seen it where like 8 questions all rely on like one measurement where like you could screw it up. But you get where I'm going here, right? Like if you mess up one little issue, like if you screw up, say, the downward force right here, yeah, the whole thing's shot. So it kind of stinks. That's why physics is hard, right? That's why there's only 11 of you left. So. Okay, let's do the second half here. Let's solve for the tension in the rope. So for the tension in the rope, we now want to work with one object or the other independently. I'm going to recommend let's work with the sled, because I actually gave you a number specifically for the sled. So now you almost need to reconsider your free body diagram again. You probably don't need to redraw it, but I'm only going to work just on the sled, which had a mass of 50 kilograms. Okay, what is working on the sled? Well, the tension in the rope is pulling it upwards. Right? What is pulling it back down? Friction, and I want to be specific, the downward portion of the gravity, the downhill portion of gravity. That makes sense? Because not all of gravitational force is actually pulling it downhill. Some of it's actually pulling it into the mountain itself. So honestly, this looks like the exact same thing we just did. Tension minus friction minus downhill equals mass times acceleration. Or to rearrange it, to find tension, it's going to be mass times acceleration plus some friction plus some downhill. We have all these numbers, don't we? Mass. This time it's the mass only of the sled. So 50. This is the linchpin to the whole thing, though. We needed to know its acceleration by solving the previous example. So its acceleration is that 0.426 number that Michael gave me. We were given friction, because it actually told us how much friction was on just the sled. I think it said it was 200 newtons. Yeah. And then for FD, this is mass times gravity times the sine. So mass is 50, gravity is 981, and you need the sine of 25. What am I saying here? Once you get the hang of how to arrange all this stuff, the math is like we got this part, hopefully. Finish it, Rebecca? What'd you get? 425? 428.5? We probably only get 3 sig digs, I'm thinking, right?
I get 2.
2 sig digs? 4.3 times 10 to the 2. Cool. Anybody else get that? You're frantically calculating this.
I don't.
4.3 times 92. Okay. One last thought here. I don't know that I'm ever going to be this screen, but it is actually possible. Oh shoot, I'm out of time here. It is actually possible to then use that tension to solve for the second box, because that tension that's between the two boxes is actually the same tension on the other box. So in theory, what I could do is ask you to then use that tension to solve for this box's free body diagram, where it would have downward force pulling it down, friction pulling it down, tension pulling it down. You guys see what I'm saying here though? You can actually then use that tension in a follow-up calculation. Yay for physics. Okay, thanks for bearing with me, guys. Tomorrow we'll spend some time working on this now, because it's a lot, eh?